And that wasn't in this. That wasn't in the. I wasn't trying to be funny. What happens here is we have to come up with a way to distinguish how polygons themselves can be similar as well. Now, today what we're going to look at, probably between today and tomorrow, we'll kind of mix this with, as we start into the triangle stuff, is that if we understand how to write out a similarity statement, very along the same lines as what we did with the congruency statement, setting up the ratios and solving for sides and solving for angles becomes super easy because it always works out to be the same setups. So here's what happens. I think the easiest thing to think of is, do you guys all agree that triangles are polygons? Now, if I do this and I just kind of do a quick two triangles, clone it, just make one bigger than the other. Is that all right? Let's do this. Let's say that we have, let's label it. We'll call it ABC and XYZ. Now, in order to say if we have two shapes or two polygons that wind up being what are called similar, you get all this different correspondence. So I can say that. Do you know what it is? What is it? The sides are, you're right, they have different sizes, but what about the sides? Do you know what that is? What happens with it? They could, but that means that if they're doubling, that means they have different, the scale factors are the same. So they have different ratios. You're dead on that one by saying if you double it. Because if I double it, can I triple it? Can I cut it in half? Can I cut it in fifths? I mean, you can do all that, but as long as it's consistent, it always works. So you're on the right track, absolutely. So what we do is we set it up just a little differently. We can say that triangle ABC is similar. We just use squiggly. Squiggly.
Is it a tilde that you call it?
Yeah. We say that those two triangles are similar. Okay. Oh. You have to. I forgot to get you started. We get you started on this thing first. You got your calculator? Let's get into that. You want to just run out the answer later. That's the second part. This is just this part. Just mark it on there, and then I don't know. Hey, sir. I'm sorry. I forgot to set that up right at the beginning. I'm old. So just like Josh was saying a second ago, and we've done this before with congruency statements, it means that the angles that match up are always going to be congruent. So by looking at the statement, I know that A and X have to be the same. B and Y have to be the same. And then lastly, C and Z would have to be the same. Now I know I kind of used a generic picture of a triangle that kind of looked the same as it is. But this goes for any shape, any polygon that you have, no matter how many angles there are, 3, 5, 8, 12, whatever. As long as you have that statement that says that they're similar, you're always going to get all the corresponding angles that are congruent. So one thing that happens, all corresponding angles are congruent. Then the second thing is the sides, oops, I'm writing it right, are proportional. And this is where it gets to be a little bit weird if you're not careful about writing out what we call a similarity statement. Excuse me. So A, B, C. You know that A. And you don't need a diagram to know this. just like when we had congruency, we didn't have to have a diagram to see it. We could go right off the lettering. We do the same thing here. But when we start talking about the similarity part with the size, this is where it becomes kind of crazy. Because remember, when you're talking about proportions, we're talking about fractions. Fractions have two parts, the numerator and the denominator. Normally what we do is, as we're reading this going from left to right, all the side lengths from the triangle on the left, or whatever shape that you have on the left, on one side, I usually keep those in the numerator, and all the side lengths on the other one go in the denominator. That way it keeps things straight, because if you start mixing them up, the ratios won't work. So if I'm looking at this, move this up just a bit, it was just by following my letters, if I say side AB is to side XY, that ratio would have to equal BC to YZ, which would have to be AC XZ. All three of those ratios have to be the same. And like you were saying, Josh, it could be double. Or like 1/5. You know, if triangles ABC had sides of 2, 4, and 6, the other one would have to have been in 12. Yeah, exactly. And that's how that works. Because all those sides would have to have that common ratio. As you simplify it out, remember we called that the simplified ratio was called the scale factor? The scale factor between the two triangles stays equivalent. Always. All right? And as you can see, what happens is we might know 1, 2, 3, 4, 5 of them. We can use those scale factors to find a missing side of a similar triangle as opposed to being a congruent side from congruent triangles. Instead of saying things are equal, we're going to have things that have ratios. So we're just going to do a ton of cross multiplying. And cross multiplying. All right? Not so bad, is it? So let's look at an example of how you would write one out. Just do this. If I look at these two, and I want to see, I want to write out a similarity statement to see if in fact they are similar. I want to write what that means by writing a similarity statement is triangle ABC, triangle BAC, however you want to start your labeling of the triangle. Does it match up to angles on the other triangle? Well, if you look at the diagram, do all three angles match? Yeah, so we know that right off the bat that all three angles match up. So that's the first thing you check off the list, that we know that it could possibly be similar. But what we have to do then is check the side ratios to see if the ratios simplify out to all be the same. So if we start on the triangle on the left, do you guys just want to start and say ABC? 1 right angle, 2 tick marks? So our assumption is that triangle ABC is similar to triangle XYZ. We know that the angles match. So take a second and, as you're writing that out, write down what those ratios of the sides should look like. Here's a hint. Looks just like the example we did. I always want to do letters first. Thanks for reminding me. We always want to go letters first, especially for these first few days, because that way it forces you to make sure things are matching up via the lettering that you start with. Because the more work you do at the beginning of this type of stuff, the easier it becomes in before as things start getting weak. Because then at that point you'll know that you're doing exactly what you start doing those slow. You pick up on it. If not, you can always fall back on the lettering. The lettering will always tell you the right way to do it. If that makes sense. Let's see. This so happens that this is the same example here. A, B, B, C. Another little trick that I would say, if you know that you have a triangle just write out the 3 side lengths in order that you would before you make your fraction, and then do that again for the next one. X, Y, Y, Z, X, Z, and those have to make the fractions and put them through. It's a nice little trick just by writing out the lettering. So let me move this up, and I'll move it back down so we can see it better. So if I say AB, actually, if I shrink up the diagram, will you guys still be able to see it? That way I can move this up a bit. You guys still see that all right? Just to give it a little space. Now that I have it written down in letters, I just write down the numbers and see if it works. Again, this is where that multi-view calculator becomes awesome because you just keep checking the same thing over and over and over again. So let's see, AB is 15. XY is 6. What are these decimals you're talking about? BC goes to YZ, so at 20 to 8. And then 25 to 10. And what we're doing is, as you go through the fractions, and Josh, you're not wrong by saying the decimal parts, but whenever we talk about ratios, we always put them in what we call an improper fraction, an improper simplified fraction. By doing it, the improper simplified fraction, it's going to help you when we get to trig in a little while. Next year in Algebra 2, we don't deal a whole lot with decimals because when you start to place things in trigonometry with fractional parts, it's much easier to count halvesies in quarters as opposed to 0.25 of this, because you can do the division quicker and things like that. It works out a little bit cleaner. So in this one here, so you just start going through it. So if I'm going through this, I'm just going to do my fraction, just do 15 over 6. Oops. Hit enter, I get 5 halves. I do 20 over 8. Hey, look at that, I get 5 halves. And then 25 over 10, I get 5 halves. So all 3 of those sides simplify to be 5 halves. So that means that since these guys all have the same common ratio, they have the same, what we call scale factor, they are in fact similar. It is 2.5, yes. All right. But what we're checking here is what's going to happen, Josh, is that instead of having to do that whole 2.5 stuff, eventually you're going to miss this part, but know that that's 15. And you have to figure out it's quicker to do cross multiplying. Does that make sense? So that's what you do. That's how you're checking to see if something is similar. If so, you just write out the similarity statement and you check the 3 fractions. If all 3 of them simplify to be the same thing, great. If they don't, then you know it doesn't work. What do you mean? That's what we were checking. We went through, we saw that all 3 of those angles matched up, so we wrote it out in terms of the angles. That was the first part. The second part is to check and see if the sides have the same ratio. Yep. So then you're checking to see if they're what we call proportional. If all the ratios are the same, then we say that they're proportional. And then the simplified version of that is called the scale factor. There's a lot of vocab in this. I didn't realize that. So it's like, I think the easiest, I think this is the most basic. The scale factor is when everything's said and done. The proportion is all the numbers to start with. The common ratios are the simplified. And the scale factor is technically the common ratio. And a partridge in a pear tree. No, I'm going to do this. Which means that they're going to get to stuff like this, where they're going to give you similarity of parts, solve for missing pieces. Not right off the bat will they just say, hey, these two are similar, find all the missing pieces right away. They will start with something like this. They'll give you a similarity statement. They'll give you a portion in this case. They're going to ask you to find a perfect. This really is a diagram version of what you did yesterday. Yesterday in class, we just gave ratios right off the bat and just cross multiply and solve. Today, they're giving you a picture to start with. You write out the portion and solve. So it's just adding on technically one step from what you did yesterday, but yet the math hasn't changed. So if I go through this, and I know that I have AB over BC equals AE over ED, well, what's AB? BC is, I don't know, so what am I going to put there? I put an X. I could write BC if I want. I can write X. It doesn't matter. I'm just going to put an X because that's my unknown. AE, 12, ED, 4. Yeah. And you picked it up. Is it, are you sure on that? You were doing the other one. Yeah, you were going that route. Yeah, there's a couple ways you can go about doing this one. One of the way, the tried and true way of just making sure you don't math wrong would be to cross multiply. So you have 12x is 24, and yet x is 2. The other way of doing that is 6 times 1 is 12. It's 2. So what times 2 is 4? So there's a couple of ways you can go about doing that. Right? And I think that's where you were going earlier. You were saying it was 2, but you thought the 3 because of the 12. Yeah, and just bring up the other side. Yeah, sorry. There's got to be at least 4 or 5 different ways to solve this one. Just remember, slow that down just a bit. All right. Again, it's not terrible. It's just you're starting with a picture to get to what you did yesterday. I think the other one, this one, just adds one extra little piece to it. You're still given the picture. You're still given the statement to start with today, and then, excuse me. Well, I'll let you see what you have to do. Give you a second to try. Figure out what you have. AB is how much? 12. All right, so AB is 12. So I have 12 is to BC. I'm just going to call it X. AE is 18. And ED is going to be how much then? How'd you figure that out? And you see what happens here is that you have a segment. You have to subtract out that. So you get that very subtle thing of where you've got some stuff from first semester where you've got the segment addition. Just got to back up to see what's left. I didn't think it's going to be too much, but it's one of those very subtle things that you've learned in the past and kind of bring back and forth. This one here can cross multiply through. If you want, could you simplify this first to make your life easier in your brain? If you wanted to. Or just cross multiply and press buttons on your calculator. There's nothing wrong with that as well. So you have 18x equals 12 times the 15. Equals whatever. Or if you
to simplify it in your head, if I divide them both by 3, you get what? I'm sorry, 3, 6, and 5. So 60, you get x's 10. You guys get that? Make sure. I think I did that right in my head. All right. Not bad, is it? This is a really good section to start, a good chapter to start second semester with to help you guys out. You know what? We actually used to, but in the new textbook, they put what did we finish with? They switched chapters 6 and 7 from the old textbook to the new textbook. So the first example we did, it was we did the triangles. Were the triangles similar? And then now we're just going to check and see. It's just going to a polygon. Just adds a couple of sides to it. So what you want to do is just, obviously you would start by checking your angles, and then you would write down that statement of, do you start at J, do you start at K, do you start at L? Does it matter where you start your angles? It does not. And then you just make sure that it mirrors the other side. So take a second and see how you want to write up your angles. After you write up your angle, is it going to be M, J, K, L, or however you want to write it? Excuse me. And then match that up, and then write out the fractions that you're going to see. After you write out the fractions, check to see if they all simplify to be the same. That's what it means to check to see if they're similar, and then by writing out the similarity statement. Okay, so take a second, try that. It's the same process by which we did the triangle, but you're adding 2 sides. What's that? How did you write up your letters? U and M. Okay. Yeah, so you would say you follow your letters. What I would suggest you do, is if you're saying M, J, the next side would have been J, K, the next one would have been K, L. I would write out all my sides from here first, and then I would write underneath it all my sides. You're doing it that way, you're not having to overthink which one's after that. You're just following the letter pattern that you start with. Does that make sense? Do it that way, because it's a little bit cleaner. You're not doing it wrong. It's just, I know for kids making mistakes by flipping letters around, it kind of forces you to just follow your pattern. I was just telling these guys over here is that they actually, I didn't catch this, they actually are telling the letterings in order. What I would do is that, you guys all agree that the angles match, right? Here's what I would do. I know I'm going to say it's J, K, L, M, just going in alphabetical order. I'm going to write down the 4 sides. J, K, K, L, L, M, J, M. What's up? Oh. Just by doing that in order, those are the 4 side lengths in order. You okay with that? I do the exact same thing with the other one. TU, UV, CW, TW. And now, those are my fractions. By breaking it apart into two pieces like that, trying not to have to go back and rematch everything over and over again, it's a little bit less work on your brain. Actually, it's a lot easier to do it that way. Bless you. Now is when I would go back and start filling in my numbers, and I would start checking to see do they actually all supply to being the same. Let's see, I have 12, 6, 24, 16, 24, 14, and 6, and 6. Like you were saying, as you start looking at it then, these fractions don't all equal the same. This is 2 to 1. What is that? 8, so that's 3 over 2. That is 12 sevenths, and that's 1 over 1. Last time I checked, those are all different. Since those are all different. Oh, speaking of the devil. Hey, look who came back. Devil. So I had a question for you.
Well, that's what I meant.
Down in the main comments, we'll leave about 7:45.
I was right. I was a good guess. So right here, we know that even though the angles are all the same, sides aren't proportional. So not. So there you go. And that's how you verify that it doesn't work, by writing out in letters to check the fractions. Okay. Again, not crazy. Yes, sir. Yeah, let me get you that. Actually, Josh, let me put up one more real quick, because I don't get these guys started on one before I do that. Do that one. Same deal. Try that.
No, I have that. I have that digital. This is yours. Oh, this is
We're a little short here. Are you guys okay if I I go A, the single tick mark, right angle, single tick mark, double tick mark? So if I go A, B, C, D, and E, if I do that. Now, on the other one, I can write it out 2 different ways. I can go S, R, V, U, T, or I can go U, V, R, S, T. Does it matter? It really doesn't, because if you look at the angles here, you have single, right, right, single, double. Single, right, right, single, double. So if I do it that way, you could probably also see that your sides, 9, 18, 9, 18, 9, 18, it's going to be clean. So I can kind of get away with saying, all right, here, I'm going to check and see if this works. S, R, B, U, and T. So, excuse me, since I'm going from left to right on my diagram, I'm going to put everything from the picture on the left in the numerator, and I'm going to put everything from the picture on the right in the denominator. If you keep that trick of doing it that way, guys, you're going to be really hard-pressed to flip-flop your diagrams around. So I'm just going to do letters first, A, B, B, C, C, D, D, E, A, E,
R, U, T, S, T.
And I'm pretty sure they try not to go any more than 5 sides with a lot of stuff to start your verifying, because then it just gets to be really pain. And then you start filling in blanks. See what we have. 18, 18, 18 to go. 18. 12 and 12. Do all those apply to be the same exact fraction? What's the scale factor? 2 to 1, very good. 2 to 1. It would be 1/2 if you went right to left. So would it be wrong if you wrote your statement as SRVUT is similar to ABCDE? It would be perfectly fine if you flip-flopped it, but then your fractions would be flip-flopped. So then no matter when you start solving for sides, you'd have to work from right to left as opposed to from left to right. I'm just going to try and keep forcing you guys to go from left to right because I know you're going to screw up by flipping things around. So don't do that. Go left to right. All right, work left to right. I think this is all we have time to do is just one last one here. And it's kind of where it all leads us to being able to get to. We're going to have a few problems today that start with a similarity statement, and then you need to figure out a missing values. So, excuse me. I apologize. I really wish I would put a shorter picture out there. Well, what we do is something like this: that we draw it out real quick. We put in our statement like you would, and knowing that you've got your sides A, B, C, D, and then you have sides E, F, G, D. What I would do first is I would write down my similarity statement with the fractions. A, B, B, C, C, D, A, B. The same thing with the number. Filling my numbers. By this saying, by that being given to us, that means that has to happen. Because they're telling you, there's your similarity statement, write your fractions. From there, we just start filling in the blanks. So according to my diagram, what's AB? 5, good. So I would say 5 is to EF, which is Y. BC, 5, FG, X, CD, I don't know, it's a CD, GD, I don't know. And that's going to happen sometimes. Sometimes you're going to have a set of sides that you don't know anything about, which is fine, it's okay. And then lastly, you have what, AD, the whole thing, is 9, and ED is 6. So here's what happens. Of those 4 fractions, which one of them has both the numerator and denominator? Yeah, 9 over 6. You guys all okay if I simplify 9 over 6 to be 3 over 2? So can I say that this equals 3 over 2? Which means that this portion has to equal that, which means this portion has to equal that. What happens here, guys, is that you're going to use one ratio of a similar side to solve for all the missing pieces. that make sense? Once you get one fraction that simplifies out, you can reuse it to solve for x or solve for y in this case. Then you do your cross multiplying. But it all starts with being able to write down those similarity statements with the fractions with the letters. If you can write the letters out, it's just filling in the blanks. Okay. So if I cross multiply that, you get what? 2 times 7.5 is what? 15, I believe. So you get 15 is 3x. Oops. Divide that out, you get x is 1. 3y is 10, so y is 10 over 3. You're done. It works rather cleanly as you get into it. You're not wrong. I'm trying to stay away from decimals as much as we can. Oh, yeah, yeah. So again, yours would just spit out 10 over 3. Something about yours like, who's got the noun? Yeah, yours would probably say 3 repeating, unless you flip it around and set it up differently. I didn't get as far as we wanted on this stuff, so let's see. So in the book, this is going to be section. Let's go. Let's just do that for now, okay? Let's do 6 of these for right now because we didn't get as far as I was hoping to get into the other parts, which is fine. We'll finish this up for tomorrow. It's all good. Did I have 7.2? No, I have 7.3. All right, we might move stuff around. No biggie. We got plenty of time. We might be able to do 7.2 and start a little bit of the 7.3 in here. So it all kind of goes, it all kind of blends together, to be honest with you. It gets out of polygons, it goes into triangles, so you're still doing the same thing, just with left sides. So, go through that. If you guys want, I've got the textbook here if you want to just take a picture of it real quick. Otherwise, you got to put it on your phone or on your Chromebook. Okie dokie. All right. Good times.